Hello everyone. In this video, I will introduce some solutions to some problems in the linear algebra homework 4. Okay, let's look at the first question. In first question, we want to find the largest possible number of independent vectors among the 6 vectors provided by the question. Now we can see that B4 equals to 0, 1, minus 1, 0, and it equals to B2 minus B2 is 1, 0, minus 1, 0, minus V1, and V1 is 1, minus 1, 0, 0. And so V2 is equals to V2 minus V1. Therefore, we can know that V4 is a linear combination of V1 and V2. Okay, let's check the V5. V5 is equal to 0, 1, 0, minus 1, and is equal to 1, 0, 0, minus 1. This is V3, minus 1, minus 1, 0, 0, and this is equal to V1. So we got that V5 is equal to V3 minus V1. Therefore, we know that V5 is a linear combination of V1 and V3. Now we can look at the V6. V6 is 0, 0, 1, minus 1, and is equal to 1, 0, 0, minus 1. This is V3 minus 1, 0, minus 1, 0. This is V4. So we know that V6 is V3 minus V2. Therefore, V6 is a linear combination of V2 and V3. Now we should check whether V1, V2, and V3 are linearly independent. So we should check the null space of this matrix is equal to 0 or not. And the first column of this matrix is V1, and the second column is V2, and the third column is V3. And if calculating, we can find that the null space of this matrix is equals to 0. Therefore, V1, V2, and V3 are linearly independent. So we get the answer is 3. We know that the largest possible number of the independent vectors is 3. Okay, let's move on to the question 2. In question 2, we want to find a basis for each of these 4 subspaces of R4. Now we look at the question A. In question A, all vectors, the components of vector are equal. So we can simply check the null space of 1, 1, 1, 1 is equals to 0 or not. It's easy to find that the null space of 1, 1, 1, 1 is equal to 0. Similarly, the null space of C multiply 1, 1, 1, 1 is also 0. Therefore, 1, 1, 1, 1 is a basis for the space of all constant vectors C multiply 1, 1, 1, 1. Now we look at the question B. In question B of vectors, the components of the vector add to 0. we can use the result of question 1 here. The null space of the matrix is equals to 0. So the null space of this matrix is equals to 0. And now we look at every column of this matrix. The first column, the components of the first column is add to 0, and it's same in the second column, and the third column is the same. So, and the first column and second column and third column belongs to R4. Therefore, because the null space of this matrix is equals to 0, we know that 1 minus 1 0 0 and the 1 0 minus 1 0 and the 1 0 0 minus 1 is a basis for the space of all vectors whose components add to 0. Okay, let's move to the question C. In question C, we want to find a basis of a subspace spanned by all vectors that are perpendicular to vector 1 1 0 0 and vector 1 0 1 1. First, we assume that the vector v is equal to 1 2 v1 v2 v3 and v4, and the vector a is equal to 1 1 0 0, and the vector b is equal to 1 0 1 1, and assume that vector v is perpendicular to vector a, and the vector v is perpendicular to vector b. Therefore, the inner product of vector a and vector v is equals to 0, and the inner product of vector b and the vector v is equal to 0 too. So we got these two equations. The first is v1 plus v2 equals to 0, and the second is v1 plus v3 plus v4 equals to 0. After calculating, we can find that v1 equals to minus v3 minus v4, and v2 equals to v3 plus v4. So we now can rewrite vector v as minus v3 minus v4, which is v1. This is v1, and v2 equals to v3 plus v4, and then v3 and v4 remain, and it can be rewrite as v3 multiply minus 1 1 1 0 plus v4 multiply minus 1 1 0 1. Now we check the null space of this matrix. The first column of this matrix is here, and the second column of this matrix is here. We can find that the null space of this matrix is 0. So we know that this 1 minus 1 0 minus 1 1 1 0 and the minus 1 1 0 1 is a basis for the space of all vectors are perpendicular to 1 1 0 0 and 1 0 1 1. Okay, let's move on to question D. In question D, we want to find the basis of the subspace spanned by the column space and null space of I. I is I is equal to 1 0 0 0 0 1 0 0 0 1 sorry 0 0 1 0 0 0 0 1. So the column space of I is equal to 1 0 0 0 and 0 1 0 0 and 0 0 1 0 and 0 0 0 1 and the null space of I is 0. So we know that this is the basis for the column space at the null space of I. Okay, let's move on to the question 3. In question 3, we want to find specific vector S. So the dimension of S is equal to 0 or 1 or 3 or 4. And S is spanned by the 24 rearrangements of vector S. And S belong to R4. Let's look at the question A. Because the dimension of S is 0, so the only possible solution of this question is 0 vector. Okay, let's look at the question B. In the question B, the dimension of S is 1, so all the elements in S are the same. So S can be written as this. Is A multiply 1 1 1 1, and A can be 0 because if A be 0, the dimension of S will be 0, and A belong to any real number. So we can choose S as 1 1 1 1. Okay, let's move on to the question C. In question C, the dimension of S is 3. To solve this problem, we first let vector V equals to 1 1 1 1. We can use the result of question 1 here. The null space of the matrix is 0. Now we back to the question 3. At question 3C, we assume that the vector S, the inner product of the inner product of vector S and vector V is 0. That means that the vector S is perpendicular to vector V, and that also means that the components in each components in vector S add to 0 because the components in vector V are all the same. So if the inner product of vector S and vector V is 0, the inner product of vector S and vector V equals to 0, we can refer to that each components each components in vector S add to 0. So we can use the result of question 1. We find Assume that the basis of S is here 1 minus 1 0 0 and the 1 0 minus 1 0 and the 1 0 0 minus 1 and the dimension of S is 3. So we can choose S as 1 minus 1 0 0. Okay, let's move on to question D. In question D, the dimension of S is equal to 4 and the S belong to R4. So the basis of S is the only possible basis of S is 1 0 0 0 and the 0 1 0 0 and the 0 0 1 0 and the 0 0 0 1. So we can choose S as this 1 0 0 0 and the basis of S, the dimension of S is equal to 4. Okay, let's move on to question 4. In question 4, we want to find the basis and dimensions for the four subspace associated with matrix A and matrix B. Matrix A is here and matrix B is here. Matrix A is equal to 1 2 4 2 4 8 and the reduced matrix of A is 1 2 4 0 0 0 and this and this are free variables and this is pivot. Now we look at the matrix. Now we look at the A transpose. A transpose is equal to 1 2 2 4 4 8 and it's equals to the reduced matrix of A transpose is equals to 1 2 0 0 0 0 and this is the free variables and this is the pivot. So we now find the null space of A. The null space of A is equals to minus 2 1 0 and minus 4 0 1 because the matrix of A has two free variables. So the null space of dimension of null space of A is 2 and the null space of A transpose is equals to minus 1. Minus 2 and 1. It's equals to minus 2 1 because A transpose only have one free variable, so the dimension of null space of A transpose is equals to 1. But we should know that the basis of column space of A is the pivot column of A. So we find that the basis of column space of A is equals to 1 2 is a pivot column of A. And therefore the dimension of column space of A is 1. Similarly, we can find that the basis of column space of A transpose is equal to 1 2 4 because A has only one pivot and its pivot column is 1 2 4. So the dimension of column space of A transpose is equals to 1. Okay, let's then solve. Let's then find the basis of null space of A. The null space of A is equal to minus 2 1 0 and minus 4 0 1 because these two are linearly independent because null space of -2, 0 and then -4, 0, 1 is equals to 0. So the basis of null space of A is equals to this, and then we know that the dimension of null space of A is equals to 2. And then we also can find the basis of null space of A transpose is equal to -2, 1, because null space of -2, 1 is equals to 0. So the dimension of null space of A transpose is equals to 1. Okay, let's move on to solve the matrix B. The matrix B is 1, 2, 4, 2, 5, 8. After reduce, we get this matrix, and this is the free variable, and this and this are pivot. Now we look at the B transpose is equal to 1, 2, 2, 5, 4, 8. After reduce, we get this matrix, and it doesn't have any free variables, but it has two pivots. These two. Now we can find the null space of B. Null space of B is equal to -4, 0, 1, because it only have one free variables. It have only one free variables, and the null space of B transpose is equals to 0 because it doesn't have any free variable. Now we can find the basis of current space of B. It's similarly as here. We know that the basis of current space of B is the pivot column of B. So we can find the basis of current space of B is equal to 1, 2, and 2, 5, because it has two pivots, and here is one of its pivot column, and this is the second pivot column. Therefore, we know the dimension of current space of B is equal to 2. And then similarly, we can find the basis of current space of A transpose. The basis of current space of B transpose is equals to its pivot column is 1, 2, 4, and 2, 5, 8. So we know the dimension of current space of B transpose is equals to 2. Okay, let's find the basis of null space of B, because the null space of -4, 0, 1 is equals to 0. So -4, 0, 1 is a basis of null space of B. Therefore, the dimension of null space of B is equals to 1. And now we find the basis of null space of B transpose is equals to 0, because null space of B transpose is equals to 0, and so the basis of null space of B transpose is equals to 0, and the dimension of null space of B transpose is equals to 0. Okay, we have solved the 4 questions in the linear algebra homework 4. Thanks for listening.